Classic tasks measuring working memory use simple stimuli such as colored squares or oriented bars, flash the stimuli on the screen for very brief periods of time, and show that only roughly 4 or 5 separate items can be remembered at a time. However, if participants are given real-world objects to remember and longer encoding times, the amount of objects they can correctly report at test is larger. This boost in performance for real-world objects is generally assumed to reflect the use of a separate episodic long-term memory system rather than working memory. However, in this controversial paper, Dr. Timothy Brady and colleagues Dr. Viola Störmer and Dr. George Alvarez argue that the benefit for meaningful objects is due to benefits in the working memory system itself, not due to contributions from long-term memory. There is a debate going on currently, if I understand correctly, about this here issue. In this short video, I am going to summarize this 2016 paper, and I hope to follow this video with the subsequent papers on this debate and turn this into a video series. The benefit of using meaningless stimuli like colored squares, Gabor patches, and oriented bars is that meaningless stimuli are assumed to best assess the core capacity of working memory because they have no semantic associations and are repeated from trial to trial, which minimizes participants' ability to use other memory systems, such as episodic visual long-term memory. Also, encoding time does not usually matter for these simple stimuli, such that whether participants are given 100 or 1000 milliseconds, they still only remember about 5 items. When participants are given real-world stimuli, especially when each trial features unique items, memory capacity expands astronomically. There are 2 possible reasons for this. Working memory for meaningful objects is getting help from long-term memory, such that the representation working memory is kind of tied to a representation in long-term memory, or if you prefer the embedded process model, activated long-term memory. Or working memory itself, for some reason, has a higher capacity for meaningful objects. To tease apart these possible explanations, the authors use contralateral delay activity, or CDA, which is a sustained negative deflection in the event-related potential that occurs during the retention period over the hemisphere contralateral to the to-be-remembered items and is typically largest over parietal occipital scalp sites. Or it's an EEG signal that occurs while participants are maintaining items in working memory. Its magnitude increases with the number of items being held in working memory, and importantly, it decreases when items are moved from working memory to long-term memory. So in this paper, the authors will measure this while participants remember meaningless or meaningful stimuli. If there is a steady increase in CDA for meaningful stimuli, it suggests that working memory capacity is not fixed to 5 items, but depends on what is being stored. Very controversial. However, if the CDA stabilizes or decreases with meaningful stimuli, then this suggests that items are indeed receiving help from long-term memory storage. For the experiments, my description here is a summary and there are additional details in the paper. I'm just saying enough here to understand the basics of how things played out. In experiment 1, participants saw 6 colors or 6 objects for 200, 1000, or 2000 milliseconds, followed by a 1000 millisecond delay. After the delay, a single item was cued and then tested in a 2 alternative forced choice format. To minimize verbal rehearsal of the experimental stimuli, participants were shown 2 digits before each trial, and they were told to verbally rehearse the digits so that they could report them after the memory 2 alternative forced choice test. For the memory test for colors, the test consisted of a forced choice between the original color and a novel color that was categorically distinct and did not appear on the original display. For objects, there were 2 conditions. In one case, an object was tested against another categorically distinct object. For example, a bell you had seen versus a cookie. This was designed to measure how many objects participants remembered. In another condition, an object was tested against another exemplar from the same category. For example, one pitcher versus another pitcher. This was designed to measure how many objects participants remembered with detail. The main manipulation here is just encoding time, 200, 1000, or 2000 milliseconds. Indeed, when remembering meaningless colors, encoding time did not make a difference, but when remembering the meaningful objects, the more time there was to encode the objects, the more that was remembered. So as a comparison, at the 2-second encoding time, about 3.7 colors were remembered, while about 4.7 objects were remembered. In experiment 2, 3 objects were presented in a semicircle in each visual hemifield, and participants were cued to memorize either the objects on the left or on the right of a fixation and to ignore the other objects. The to-be-ignored objects consisted of the to-be-remembered stimuli from a different trial. Thus, across trials, the exact same visual displays are presented on the to-be-remembered side and the to-be-ignored side, thus equating all perceptual information so that any brain differences between the cued and uncued side were due to differences in memory processes, not perceptual processing. The cue indicating which side of the screen to remember was an arrow pointing either left or right that appeared at the center of the screen 1000 milliseconds before the presentation of the objects. The objects were shown for 200 milliseconds or 1000 milliseconds. After the objects were presented for this encoding duration, there was a 700 millisecond delay interval and then a cue indicating which of the 3 memorized objects would be tested. The cue was visible for 500 milliseconds. Finally, the forced choice test was presented and remained visible until the participant made a selection. Here we are looking at the CDA during the retention or maintenance interval. Again, we find better performance with the 1000 millisecond than the 200 millisecond encoding time. They also, in fact, found larger CDA for the 1000 millisecond encoding time than the 2000, suggesting that participants are indeed storing more in working memory. In experiment 3, in each block, participants remembered either 3 objects, 5 objects, 3 colors, or 5 colors. On each trial, the to-be-remembered stimuli were presented in a single visual hemifield, and a matched set of stimuli were presented in the other visual hemifield. This matched set of stimuli was from the same condition and represented the to-be-remembered stimuli from a different trial, thus ensuring that the exact same visual displays were presented as to-be-remembered and to-be-ignored across trials. Participants were cued to memorize the to-be-remembered stimuli with an arrow cue at fixation that appeared at the center of the screen 1000 milliseconds before the presentation of the stimuli. Following the arrow cue, the stimuli were presented for 1000 milliseconds, followed by an 800 millisecond delay period, and then a 500 millisecond cue, indicating which of the 3 or 5 memorized stimuli would be tested. Finally, the forced choice objects or colors were presented and remained visible until the participant made a selection. In experiment 3, we are comparing the CDA for the meaningful objects with the meaningless colors. They did find a larger CDA for the objects than the colors. But perhaps, does the CDA just react more to objects for some reason than it does for colors, regardless of how many individual items are stored? They had an additional control experiment where participants only had to remember 3 objects or 3 colors. So if the CDA reacts more to objects, the CDA should be larger here for the objects. They actually found that the CDA was a bit larger for colors, supporting their conclusion that the CDA in their main analysis was tracking working memory load, and that working memory load was larger for meaningful objects than meaningless colors. The authors make the case here that the benefit in working memory for meaningful objects is due to enhanced active working memory storage for such things, given there is enough time to encode them. They say that it is still possible for episodic long-term memory processes to help out, but that it doesn't explain the benefits reported here. I'm going to just quote their final couple sentences because they said it really nice. These results demonstrate that working memory capacity is systematically underestimated by using simple stimuli about which we have no existing knowledge. Our findings also raise important questions about the functional role of the visual working memory system. In particular, they raised doubts that the entire function of visual working memory can be to persist information across eye movements, because the system seems to continue to accumulate information on a much longer time scale than typical fixation durations. What do you think? If anyone here is familiar with this hot off the press paper by Park and Ah, then you will be intrigued by the paper we just summarized here. There is many more studies that follow up these results, and hopefully it will be less than a year when I'm able to make a video on the next one. The link and citation to the paper is in the video description. Thanks for watching, and no AI was used in the creation of this video.